Hello wonderful person, this is Anton, and today we're going to be talking about the expansion of the universe. And more specifically, I wanted to talk about this new technique that one of the scientists discovered that can once again be used to try to calculate how fast the universe is expanding. But let's actually talk about this idea in general, just so that we're all on the same page and just so that you understand why we think the universe is expanding. And I think here the best example I can give you is essentially by just trying to zoom into this dark location right there. As we start looking closer and closer into the depths of space and into the ancient universe, we'll start discovering certain galaxies that appear to be much redder than everything else. They'll be what's known as redshifted. And from general observations of other phenomena, we know that redshift usually implies that something is moving away from you really fast. And so back in the 1930s, scientists were trying to figure out what's happening with the light here at these really far away distances. And actually one of the propositions initially was what's known as the tired light hypothesis, which essentially implied that the light just kind of gets tired and becomes redshifted as it travels across space, but the size of the universe itself is more or less fixed and it's just the light that changes. In other words, nothing in the universe was expanding, everything was more or less fixed, and there was some other explanation needed to trying to understand why certain galaxies were so much more red than other galaxies. But then we had several interesting tests, including the very famous Tolman surface brightness test, which more or less disproved this idea. The idea here was very simple. If the light was indeed tired, then by looking back in time, we should be able to see pretty much the same amount of galaxies, with the overall brightness being intact, and the only difference being that they're all red. But then it turns out that if you were to look back in time, and if you were to start looking deeper and deeper into space, you would actually start seeing a lot less galaxies, with the only explanation being that the universe indeed expanded and they essentially moved farther and farther apart. But today we know that it's not just expanding, it's also accelerating in its expansion, and this is something that was only discovered 2 decades ago and something that resulted in the Nobel Prize as well. And for many years now, the scientists were trying to calculate how much all of this is accelerating by, and also trying to discover the mysterious Hubble Constant, which is the parameter of the expansion, or actually accelerated expansion of the universe. And at first everything was making sense. The Hubble Constant was defined as 68 km per second per megaparsec, which of course suggested that every million parsec, or every 3.3 million light years, the expansion of the universe was accelerated by about 68 km per second. But in the last few years, this value started to be questioned because apparently different types of measurements resulted in different value for the Hubble constant. For example, when measuring Hubble constant using various types of supernova and various types of unusual stars known as Cepheid variables, the constant was measured to be about 73 plus minus about 1.7. In other words, it was slightly higher than 68, and what's really strange is that these values were extremely accurate and the error value was not actually meeting the number 68 at all. It was way off. But at the same time, when trying to use another technique, which used the earliest light in the universe, the so-called cosmic microwave background, the value was indeed about 68 km per second, so in that sense it actually matched correctly. But both calculations were extremely accurate, and as a result, this created a kind of a crisis. We refer to this as the Cosmological Crisis today, because nobody really knows why is it that the values are so different, even though the actual difference is very minimal. But because we know that both values are actually extremely accurate, it doesn't seem to make sense. And so other techniques started to be proposed in order for us to measure this expansion of the universe or the acceleration of the expansion, and other techniques are now being tested to see what value we get from them. For example, one such technique is relying on the measurements from gravitational waves when 2 neutron stars or 2 black holes or a black hole and a neutron star collide. These gravitational waves produce very accurate observations and can actually allow us to eventually, once we have enough data, calculate the expansion of the universe as well. But for this we actually need to wait a few years and collect a lot more of these collisions, and also a lot of really precise calculations for each collision for the scientists to be able to answer the question how fast the universe is expanding again. But luckily for us, another interesting technique has been just proposed and developed, and it also once again shows us that we can calculate the value using slightly different metrics. And for this technique, the scientists, whose paper you can find in the description below, relied on a very well-known technique known as gravitational lensing. The technique that usually produces pictures like this and something that we are very familiar with. This is a technique when a massive object is placed in front of another object, and the actual mass causes the gravity of the object in front to essentially bend the light, creating a lens. With some of the more unusual objects like this one right here, today being referred to as the Einsteins Cross. And the idea here is very simple. We know that when the gravitational lens is formed, it's not always perfect. As a matter of fact, it's not really always aligned. In some cases it's shifted to one end or the other, and so the light from both sides is going to take different time to reach planet Earth. So for example, let's just say the light is about to leave the distant object and starts traveling toward us. You can see that it actually arrives to Earth at different times. Anywhere from a few weeks to possibly even a few months difference. And because of this difference, we can then very accurately calculate the distance to this distant object. And then using this distance, we can start establishing more or less accurate speed of this object receding away from us. So here we can very accurately measure the redshift of each of these distant objects, allowing us to very accurately also calculate the Hubble constant using each of these objects. And by using 27 separate gravitational lensing objects, and then focusing on 6 specific ones, the value was discovered to be about 71 plus minus 2 to maybe 3 kilometers per second. So basically somewhere in the middle between the original value we had and the new value. And so here it's basically important to understand that the value is still somewhere in that range, but we're just having trouble identifying exactly what it is. And for all we know, maybe, just maybe, it is actually different across the universe. There have been suggestions that it might have actually changed with time, and essentially either A, it sort of increased in value over the last 13 billion years, or B, for some reason, we're located in the region where things seem to be moving a little bit faster. But the other important implication here is that now using new telescopes, such as the beautiful Vera-Rubin Observatory, we'll be able to narrow down these values even more once we collect more of these gravitational lenses and apply more robust calculations to various gravitational lenses. By using this with thousands and thousands of different galaxies and quasars, we'll be able to narrow down the value to the point where it's going to have almost no error, and after this it might either resolve the cosmological crisis or, well, maybe create a new one, depending of course on what number we get at the end. For example, today we believe that approximately 4 billion years ago, which would be somewhere right here on this map, the universe started to expand a little bit faster, for, once again, reasons unknown to us. And so in that sense, maybe this acceleration and the expansion of the universe is just not constant at all. It possibly just changes with time and seems to either decelerate or accelerate as we go through the universe's age, which in itself creates yet another mystery for us to deal with. But I guess for now, all we can do is just continuously watch the skies, learn new techniques, and try to improve our understanding of the universe. Although for now, it's just something we can't really answer. We're just gonna have to wait a little bit. Anyway, on that note, that's all I wanted to mention. Thank you for watching, subscribe if you still haven't, share this with someone who loves learning about space and sciences, maybe come back tomorrow to learn something else, and maybe support this channel on Patreon or by buying the Wonderful Person t-shirt you can find in the description below. Either way, I'll see you tomorrow, space out, and as always, bye bye.